I think when more people are joining, I think we can get started. So, hello everyone. Welcome to the CPGIS 2024 educational webinar series. So this year's the webinar series theme is about GI science and energy and environment. So today is the second webinar. So it's my great pleasure to introduce Professor Xiaojiang Li from Temple University. We talk about geospatial data science for urban environmental sustainability. So before Dr. Li gives his talk, please allow me to briefly introduce Dr. Li. Dr. Li is currently assistant professor at the Department of Geography and Urban Studies at the Temple University. He was a postdoc fellow at the Department of Urban Studies and Planning at MIT, and he has been well known as one of the 50 rising stars in the geospatial world, and his research mainly focused on urban analytics for sustainability, so which is a key theme of this talk, spatial data science, urban resilience to climate change, and high-performance urban computing, geovisualization, among others. So one of his well-known projects at MIT was the Treepedia project. I think many of us may hear this project. If not, this project, led by Dr. Li, was among the first to utilize Google Street View images and machine learning or deep learning to the urban environmental greenery mapping and analysis. So actually, his work has been funded by National Science Foundation and also Microsoft AI for Earth grant, and to investigate those important issues, especially for those underrepresented community under climate resilience. So it's my big pleasure to present to you Dr. Xiaojiang Li, and I also got his permission. It's a great news to share with our CPGIS community is that Dr. Li just accepted a new position at the University of Pennsylvania, which is a great university, and he will start a new position next year, right? So now it's it's time to give you welcome, Dr. Xiaojiang Li.
Great. Thank you so much, Song, and for the warm introduction. So it's my great honor to be here to talk about some of my recent work about geospatial data science and urban environmental analytics, urban environmental sustainability for today's topic. So my name is Xiaojiang Li. I'm currently at the Temple. So here the outline of my today's presentation. I'm going to first introduce about myself. Just let you, some of you may never heard about me, so I'm going to introduce about myself. And then I will talk about my research aims to let you guys know what I'm trying to do, what my philosophy in research. And then I will also introduce several of my research projects to just give you solid examples about how I use geospatial data science for urban sustainability studies. All right, about myself, I'm currently assistant professor at Temple, but in July, I'm going to join University of Pennsylvania in the MUSA program. It focuses on urban spatial analytics. I was a visiting professor at Johns Hopkins when I was on sabbatical last year. So before that, I was postdoc at Sensible City Lab at MIT. So I get my PhD degree from Geography Department from University of Connecticut, master's degree in Institute of Remote Sensing and Digital Earth Chinese Academy of Science, and then bachelor's degree in environmental science and planning from Henan University. So I get a pretty diverse background from environmental science to GIS to remote sensing to planning and earth science departments at Johns Hopkins before. So I have pretty different backgrounds. So in my previous life, working at a Sensible City Lab, so you can find a daily life look like as a geospatial data scientist and also urban scientist. So we are working on using sensors, different kinds of sensors to deploy that anywhere in the city and to monitor the infrastructure, to monitor the sewer, monitor the air quality, and so on. So we also deploy autonomous boats, we call that rowboat in Amsterdam, that kind of infrastructure to support the transportation in Amsterdam. So my research aim actually focuses on urban areas. So here I just want to show you about 4 numbers. The 2 mean they are only 2% of world landmass for the urban areas. Urban area is pretty small compared with the landmass for the whole world. But urban areas are home to about 50%, maybe more, of world population. And cities also consume about 75% of global energy and produce about 80% of greenhouse emission. So you can find urban areas is really very important for our humanities and also for our sustainable development. So my research philosophy actually is try to utilize sensing technology or data-driven method to understand the dynamics in our social environment system in our cities. So for example, nowadays there are so much data available in our cities to represent the dynamics in our cities. Like we get autonomous, we get a lot of CCTV cameras everywhere. We get wearable devices, your smartphone actually get a lot of sensor, GPS-enabled devices, and all these kind of sensors can help us generate huge amount of data to represent the dynamics in our cities and also provide huge opportunities for us to understand our cities and also help us to tackle the challenge we have in our cities. So my research actually try to combine science, data, and design together through engagement with local communities and make our city more livable, healthier, equitable, and sustainable. So, so here I just show you about a word cloud about my work. You can find my research actually focus on urban area using data-driven method, focus on environment studies and planning design as well. So I'm going to just then use several solid examples to show you how I combine data science design together and tackle or review some of the urban environmental problems. So the first project I'm going to talk about is mapping street greenery. So we all know that the trees are very important for our cities. It makes our street more beautiful, greener, and more walkable. So here just show you one picture and you can find it's just beautiful and makes street better place to walk and also provide some other social benefits. But you should not expect all street as green as this one. But sometimes a little bit of greenery could make a big difference. Like in this case, you can find, some greenery can definitely make your street more beautiful, also probably more walkable, just better place. So traditionally, or maybe even still today, a lot of people may, do the kind of field work to do survey, point by point, tree by trees, to monitor and measure the parameter for trees. But this kind of work is very time consuming and also very expensive. So we just think about using high resolution area imagery to do that. So here is kind of area imagery, and for one city, we can easily, calculate the tree can be covered or some other metrics to represent the greenery and the distribution of greenery. But that kind of big problem with using that top-down view method or traditional remote sensing method. That kind of top-down view, that's not human view. So that, if you walk along the street or in the cities, your experience may be very different from what you see on the satellite imagery or the area imagery. So based on this simple idea, actually, I was thinking, can we use some some other method to quantify how green is your street or how much greenery you actually can feel or can see on the street? So I just think about using Google Street View to do that. Well, if you have never used Google Street View, you may also think there are several other options like Baidu Street or Tencent Street or some other street service available as well. So if you check Google's documentation, you can find they do have kind of URL or API method to help you to get the Google Street Image at different direction for different locations. So here I just specify several parameters marked as red color. So put them, change the parameters, you can get image at different directions or different locations. So these are image captured in New York City. I think many are pretty familiar with this. So, Google Street View become available worldwide, and the data set had been accumulated for about 17 years. 14 years, start from 2007 to the most recent. So it provides huge repository for us to study, the change of our cities, and also how the streetscape look like at hyperlocal level. So we can use machine learning, or more specifically, deep convolution neural network, to segment the street level image into different categories. We can extract different information. Like if you focus on trees, you can just extract greenery. If you focus on the pavement, sidewalk, or buildings, you can do that. Or if you want to check the openness of sky, or you can just extract the sky pixels. So here, just show you about the original Google Street View panoramic image, panorama, and then the kind of segment image, and then you can also generate hemispherical image. I will show you how to use that image for further analysis later. So here, well, if you don't want to use Google Street View image, actually you can just use your phone and mount your phone in the car, and you can capture image. So they kind of I use my phone as dash cam and get the image and use machine learning method to extract different objects from the streetscape image. So actually, I propose a very simple metrics to quantify how much greenery actually can see on the ground. It's called green view index. So basically, just calculate the average of percentage of greenery for image captured at 6 different directions, just to represent how much greenery you actually can see or you actually can feel on the ground. So here is the pipeline to generate the green view index based on street map. So on the top left is the street map, and then I create sample site along street, and then put the coordinates of the sample site to Google's API, and you can download the image at different directions. So then you can use Google Street. You can use machine learning method to extract the greenery or tree canopy covers from those image and calculate the green view index. So if you still feel confused of what green view index really look like, so here there are 5 sites. Hopefully that help you understand what the green view index of different values may look like. So the first row is for the one side in Boston. You can find the green view index value is about 36, and a lot of greenery, and the green view index value is pretty high. If you check the bottom row, so very little greenery over there, and the green view index is pretty low over there. So I further developed a project called Treepedia. So many of you may have heard about that project. We developed that a while long ago. So if you're still interested, go and check the website. So here's kind of video to show you about the project. Actually, we are driving through Google Street View image from Boston side to Cambridge side. So for example, here we're actually driving wrong direction. Yeah. So because these are screenshots of Google Street View image. So we use computer vision algorithm to recognize the tree canopy covers from the image, and then we can calculate the green view index. Well, if you're still interested in the project, go and check the website. We also open source the dataset, open source the code. So if you're interested in, you can go and check it. So the second project I want to talk about is about Shade Finder. Actually, the collaboration with my former colleague at MIT, and he's currently professor at University of Tokyo. It can also called Higage, the Japanese name. So we all know that our city are become hotter and hotter. It become kind of, a really prominent public health hazard. They have to have kind of report show that the extreme heat actually kill more people than any other environmental hazard combined. So in this project, actually we are using Google Street View panorama image and to generate the shade and also map the shade. So for example, here's the pipeline to get the image. On top left is the sample site I created in Boston area. And then I get the panorama image, and then I use some kind of projection transform to generate from the panoramic image to the hemispherical image. It show you about bottom up view of your street. So some image, the Google Street image were captured in different seasons. So we only select the image captured in the green seasons. So here it kind of math behind that, how to do the projection transform. So if you read that, it's pretty easy actually. You just the basic math in high school, you can do that. So we generate the hemispheric image for all sample sites in Boston area. So here to show you about what the bottom up view of Boston streetscape may look like. So then we use this kind of PSP nets to segment the street level image. I think this one get very good performance. That reason I choose that. They have very good results. So here just show you more about what the image might look like. On the far left is original Google Street View panorama. In the middle one is kind of blended, just overlay the segmented result on top of the original image. And on the right side is the segmented results and project that into bottom-up view, hemispherical view. So here more about that, show you, actually the view may be contributed by the building, may be contributed by trees. They are actually different. So based on this image or this bottom-up view of streetscape, actually we can do a lot of work. We can simulate the solar position. We can simulate how much radiation reaches the ground and how much heat people on the street can feel or can get exposed. So here that just show you to overlay the solar position at different hours of different days on the hemispherical image. You can find, at different time or one day or different days, if the red dot is the solar position, if the red dot is behind the trees or behind the buildings, that means they are blocked. That means you are shaded actually. So based on this method, we generate the shade map at street level in Shibuya, so Shibuya in Tokyo. So you can find at different hours. The green line represents, they are shaded. The red line, I mean, they are not shaded at a certain time. So we further conduct kind of simulation just to simulate, put the kind of origin and destination. We compare with the shortest or the most shaded route compared with the shortest path. We find using our method based on the shaded path, we can help people to reduce their solar position or reduce their heat exposure by about 35%. So, maybe in future, you can just use the phone and find the shortest, not just the shortest path, but the most shaded path, especially during hot summer. So here kind of a video to show you about the Hikage project. Just show you what about the Shibuya look like in Tokyo. Maybe you can go to the long video. I'm going to show you the most important one. All right, the third project I also want to introduce about sun glare is still Google Street View related. Well, I think after this one, I will talk about my recent work about heat modeling. So I don't know if you experience this, it's called sun glare, like when you drive or walk from the west to east at the morning time or east to west at sunset time. You may find the sun is dazzling. It just make driving or walking difficult because you cannot see things before you. So actually, they do have kind of report show that about there are about 16% of environmental hazards related crashes are attributed to sun glare in the United States. But actually, we don't know when and where the sun glare happen, and there's no universal or accurate method for you to predict the occurrence of sun glare. So I get this idea based on my personal experience. I drive to Walmart and go shopping, and I realize, sun dazzling, it makes my driving super difficult. So I have to pull over and wait for a while, and then I move forward. So based on this experience, I'm thinking, can I make a method or develop some tools to help us to predict and about where and when the sun glare is going to happen? So I didn't realize actually the very simple question. Actually, you can solve that easily using Google Street View image and machine learning method. So for example, we can predict the solar position at any certain time, and for any driver in the car, or let's assume that driver, so we can just do some geometric analysis and find what the relative position of the solar position to the driver. So here, it kind of for on the top one, A and C, kind of the profile with the vertical profile. So you can find the solar position over here. If the driver is driving toward the sun and also the sun is not too high, in that case, they may find the sun it goes through the window shell and make the people feel the sun glare. So the bottom one actually is the top-down view to just show you about the horizontal direction, because the sun may be not in your window shell, so the horizontally is not in your view field. So in that case, maybe also not get sun glare. So the third thing you probably need to check whether the sun is blocked. Let's assume that the sun is very low and also in your view field. But the sun is, if the sun is blocked by buildings or by trees, you probably not feel sun glare as well. But how do we check whether the solar sun is blocked by trees or buildings? Well, we can just use Google Street View to do that. Like we can use Google Street View panoramic image and segments, like in this case, focus on the sky pixels. And here just show you what the segmented result look like on the panoramic image in Cambridge. So we can then overlay solar position at different days or different hours or 1 day on the segmented panoramic image. So here you kind of binary image, like black is obstruction pixels and white is sky pixels. If the solar position is low enough and also in your view shield and also not on the black pixels, in that case, you may have sun glare. It's a very simple idea, very simple method. But if you get the idea, you can do that very quickly. So here, just show you about the sun glare maps in Cambridge. So if you're interested in the methodology and also the result, go and check the paper we published in TRC, Transportation Research, and see. So I further developed kind of demonstration visualization to show you the sun glare occurrence for all state highways in Florida. So you can find at about 6 p.m., like 6:30, a lot of state highways orient east and west direction, they get sun glare. But after 8 p.m. or 7 p.m., the sun glare is gone because the sun just set. So actually, I also developed kind of mobile app. So it called Sun Glare. It's available on App Store. If you're interested, go and check it. It's called Sun Glare. You can download that, and it will give you information about the sun glare and also give you alerts if you do that. So I just talk a lot of applications using Google Street View. Actually, that's based on my previous work. Well, I also want to introduce some of my recent work is about urban heat modeling and mapping. So urban heat island, we all know that our city become hotter and hotter. I give you the picture, but I think most of our current work, they are still using land surface temperature method. So we use a land surface temperature derived from, let's say, landslide or MODIS or eco stress or different kind of sensors. We can easily map the spatial distribution of the heat, at massive scale and continuously. But they're kind of big problem of using the satellite-based method. So first one, this is surface temperature. They're not human heat stress. Just give you one example. So the surface temperature may show you about how hot of your roof, building roof, but actually nobody live on top of a building. So it doesn't make any sense to use the land surface temperature to indicate how much hot people actually can feel. The second big issue is the coarse resolution. I think the highest resolution thermal imagery you can get probably from land side. The resolution is about 100 meters. So it's pretty coarse, especially if you want to see check that heat distribution in the cities, street by street, neighborhood by neighborhood, that may be very different. But if you use 100-meter resolution, that's just way too coarse for that. The third big problem is fixed observation period. So for example, in Philadelphia, the city where I'm currently based, the land side will go over to the city every 16 days at about 11 a.m. At that certain time point, that's every 16 days. That means I can only check the heat map for that certain time point every 16 days. But actually the heat, the temperature change a lot in one day and day to day. So using that method, it definitely cannot show you about how hot or a different time point. So just do a little bit more literature review about different heat metrics. Other than land surface temperature, they also have some other heat metrics like air temperature or mean radiant temperature. So we all know that air temperature, the mean radiant temperature is kind of metrics, and not just consider air temperature, but also consider the radiation that the person may exposed. So for example, one person, if you stand in the shade or not in the shade, the air temperature may be very similar, but you may feel very different. In the sunlight, if you are exposed to the sunlight, you may feel much, much hotter. But actually, these metrics, this feeling cannot be indicated by the air temperature itself. So, well, for the air temperature, we can generate that very easily. I know in the US, NOAA have kind of campaign to use urban heat mapping. So I very thought about this method. So it's probably good for public education, but should not be used for scientific applications because the lockout sensor is not accurate, and a lot of people they are not trained for this. Like they expose the sensor to the sunlight, they may get extremely high temperature, but that's just not right. So for the land surface temperature, I understand why people use that method because it's so easy to get. And you can just write a very simple line, several lines of code in Google Earth Engine. You can calculate land surface temperature at large scale. It's good to use, but it doesn't mean it's right to use that. So here's the interface of using Google Earth Engine to do that. So just go back again, the human feeling actually is very complicated. So this picture is, I took that in Connecticut, in farmland in Connecticut. So you can find those cows, they are smart. They know where to find the shade. They know, the shaded area is feel much better than the unshaded area. So in that case, you may find air temperature are the same, but even the cows know they're a big difference. So we probably need to think about using better method to quantify how much heat that person actually can feel. So that's about mean radiant temperature. So here's a kind of conceptual model to understand mean radiant temperature. So the mean radiant temperature consider about the radiation that a standing person exposed at different directions. That could be the direct solar radiation from the sun, could be the reflected radiation from the ground or from some other object. It could be short wave radiation, could be long wave radiation as well. So they do have several software for you to do that, like the Raman model. Well, if you do that, if you do biometeorology study, you may find the Raman model is pretty classic and is used by many people. And the second one is NVMAT. It's usually used by landscape architects that conduct analysis. Usually, that they want to build more thermally comfortable buildings and neighborhood or blocks. They conduct the simulation over there. It's kind of commercial software. So the Xiaojiang model is an open source model and also more GIS friendly. So you just need to input the GIS data like heights of buildings, height of trees, and some other land surface parameters. You can generate the mean radiant temperature. A common thing of all of these methods is that they are just super slow. It's impractical to run for urban scale studies. So here is kind of the pipeline to calculate mean radiant temperature using the Xiaojiang model. On the left side, just like I mentioned, it's GIS friendly. So you can just use the trigonometric height model, building height, and ground cover. You can then simulate the solar position at different time and and simulate how the solar radiation reaches the ground and get people exposed. And then you can calculate the mean radiant temperature just like on the right side. So in order to do that, you also need to do a lot of ray tracing actually to simulate like how the solar radiation being blocked without being blocked by trees or by buildings. Here just one example to calculate sky view factor based on the building height model. Here just show you conceptual model, how to do the ray tracing. Basically, you just simulate different directions at pixel level. But the ray tracing is very slow if you do that. Actually, my former advisor at MIT Colorado, he actually famous for his original work in this area called shadow casting. So when he did his PhD in Cambridge, University of Cambridge, he developed a kind of revolutionary method called shadow casting method. That about 20 times faster than ray tracing method. So that was about 30 years ago. But even today, a lot of people still using that method. They're not much advanced in this area. So I propose kind of a new method. Well, I would not say a new algorithm, but I would say it's based on new computing framework. Using GPU accelerated method to accelerate the whole process to conduct the simulation at pixel level. If you're interested, go check my paper published on theoretical applied climatology paper. If you know GPU, there's just a lot of independent computer units that make it super efficient for the pixel level analysis because pixel by pixel you can do the calculation independently. So I test that on my computer, and it showed that using the GPU-based algorithm, it get about 400,000 times faster than the traditional CPU-based method. So here's how I conduct the analysis. I just bought a kind of a low-cost GPU, secondary use GPU, and plug in down my PC and conduct simulation. So it's just like regular GPU can turn your PC into a supercomputer. So then I conduct analysis in Philadelphia. So I generate the building height model and tree canopy height model. I use the LiDAR data. So here's what the LiDAR data, LiDAR cloud point may look like. And so for the whole Philadelphia area, I also generate collect the land use the land cover maps. But even though you get very efficient algorithm method, but it's still not enough to memory enough to run for the whole city. Therefore, I cut the city into a lot of small tiles, and just calculate tile by tile. When I get the result, I mosaic them back together to get full picture for the whole city. So if you conduct the ray tracing, you may also get kind of aging effects. So here I create kind of buffer for each tile. But when you mosaic them back together, just chop them off. So at the beginning, I claimed that land surface temperature is not good. So here the comparison of the two metrics. On the right side is mean radiant temperature at exact same time as when the satellite go over Philadelphia and capture the thermal imagery. So you can find on the land surface temperature 100 meter resolution, you basically cannot see any difference. But if you check the mean radiant temperature I generated using my method, I can show you about the shade, the shadow, and the shadow by buildings, shadow by the trees. So I further conduct analysis, for different land use land types. I want to see what the contribution of building footprint, tree canopy cover, impervious surface, or road pavement, what the contribution of different land use land cover component on the discrepancy between the land surface temperature and mean radiant temperature. So here kind of scatter plot. I don't want to give too much detail about it, but I can show you about the major conclusion. So the comparison show the result that the land surface temperature majorly show you about the temperature on top of a building, but not on the open land on the road, that the major human activities happen. So, and also the mean radiant temperature, because conducted by simulation, you can generate for any certain time. Here just show you, we can calculate the hourly level mean radiant temperature at spatial resolution 1 meter for the whole city. So here, one work I conducted for Philadelphia, I generate one summertime at hourly level every hour, like from 10 a.m. to 4 p.m. every day for 30 days I generate the aggregated mean value for the whole city. So you can find the general distribution of mean radiant temperature in Philadelphia with spatial resolution of 1 meter. You can find a different neighborhood that may look very different. So I also generate kind of a project called Heat Expo. I generate for many cities like Boston, San Francisco, DC, Chicago, Seattle, Baltimore, and many more. So with special resolution 1 meter. So here is kind of video to show you about the project I developed. Like if you want to go to the University of Pennsylvania, so type in the address over there, you can get the heat exposure level over there. So for other cities, it's also available. If you're interested, go and Google Heat Expo, you can find the website. So here's the 1 meter resolution at the hourly level heat exposure in downtown Philadelphia. You can find at different hours that may feel very different. How you can see how the shadow, how the shade, the temperature has changed at different place over time as well. So well, automatically you want to see which neighborhood is hotter and who are living in this neighborhood, right? So therefore, I conducted the zonal statistics, just aggregate the pixel level to the sensor tract level to compare with other socioeconomic variables. So, well, first one, let's check what the landscape features and how different landscape features impacts the mean radiant temperature. So on top left, you can find the tree canopy cover has very significant and negative correlation with heat exposure. That means more tree canopy cover help lower the mean radiant temperature. This one is the height of tree canopy cover. So higher trees, that means also have lowered the heat exposure. So for impervious survey, they significant. We all know that they're nothing new, but here we just check that at a much finer resolution at a hyperlocal level. So I also conduct with social environmental analysis, compare with different socioeconomic variables. So here you can find the income is very significant and negatively correlated with the heat exposure. Proportion of people with a high school degree is positive and significant, and proportion of people with bachelor or high degree is significant and negative. And racial and ethnic variables, non-Hispanic white is negative and significant. Hispanic is positive and significant, but for Asian American and for African American, they are not significant at all. So for the different age groups and people under 18 years old is significant and positive, and older people actually is negative and significant. So here kind of further, control different variables, conduct the regression analysis. Maybe I can just go to conclusion very, very quickly. Generally, there are no significant disparities in terms of heat exposure in different racial and ethnic groups in Philadelphia. But the high-income people that tend to live in cooler neighborhood, and also the older people, they also live in cooler neighborhood. So here the kind of comparison of land surface temperature and mean radiant temperature. I also give you information about that, but here's the conclusion. So using finer resolution mean radiant temperature, it just able to detect much more detailed information about urban heat. And also land surface temperature based on satellite imagery cannot disentangle the heat contribution from different land use components like building roof, tree top, or grassland or open land. The land surface temperature has stronger correlation with the building roof. Maybe not good to represent how much heat exposure you actually can feel on the ground. So the mean radiant temperature can be calculated at a higher temperature resolution, at hourly level, at 1 meter resolution, right? So the GPU method is super efficient. So you may think about that in your future work, modeling or analysis. It's just way more efficient. And this is the finest resolution heat map we have ever generated, I think worldwide probably. So, but currently I only generate for US cities because I'm based in US and a lot of data are just available. US have very good data infrastructure, so I can generate that automatically for those cities. So I also want to talk about the heat exposure project and go that very quickly. I think I may go over time. I will be a little bit quicker. So I know some of you may use your smartphone or some other wearable devices to record your daily trajectory, or well, sometimes some app may track your position. So this one, we just utilize the data and So I'll see here kind of video to show you about the data. So here in Boston area, you can find which street or which area get more runners or people are walking along street. So here for San Francisco, we collect the data from the mobile app for these two different cities. So based on this data, we just want to combine with our heat modeling method to see or to check, or maybe also test the framework to estimate the heat exposure of individual person. So here we collect the NAP imagery, National Agricultural Imagery Program, a kind of multispectral image, and also the LiDAR data to generate the building height information for the Boston metropolitan area, with Boston, Cambridge, and several others near satellite towns are included. So it generates the mean radiant temperature at 1 meter resolution every 10 minutes for the whole Boston metropolitan area. So here just show you what that look like at different time point. So while here kind of overlay of the one human trajectory on top of that, maybe this one to help you better understand how that works. So let's say one person start from here and walk or run along Charles River and then return home. So we can separate that trajectory into different segments by every 10 minutes. And then you overlay the trajectory on the mean radiant temperature you generate every 10 minutes, and you can calculate the accumulated heat exposure for that individual person. So based on this idea and also this framework, we ran that for all the data we collected from July 15th to August 15th, 2015. So there are about 1,600 female runners, about 1,800 male runners. So here on the left side, the map, which area get more runners. So here the histogram about the duration of the running. Different people may have different running duration and distance. You can find generally the running duration is 20 minutes to 40 minutes for most people. So the distance is about 1,000 meter to 2,000 meters. So here just for different age and gender groups, because the data we get that for different age and gender groups, you can check the running duration and running distance for different age and gender groups of runners or maybe walkers. So we can calculate the accumulated heat exposure for each trajectory based on each trajectory for each person. So we use KW test and show that those runners in age group of 48 to 55, they have significantly higher heat exposure than people in age group of 18 to 24 and age group of 25 to 34. So you may also want to see what the difference between female runners and the male runners. Well, here just show you about this histogram of male runners and female runners at different age groups. So generally they all fall into the range of 1,000 degree and minutes to 2,000 degree and minutes. So we also use bug plot and test what's the difference for female groups at different age groups and for male groups at different age and gender age groups. So I can show you the conclusion. So there's no significant difference in terms of heat exposure between male and female runners in Boston area. But for female runners, the heat exposure in age group of 45 to 64 to 54 actually is significantly higher than runner in age group of 18 to 24 and 25 to 34. There's no significant difference in terms of heat exposure among other age groups. And the heat exposure is not significantly different for male runners at different age groups. The female and male runners at different age groups, they are different. So implication of this kind of work, so you can find this kind of general computing framework. It can be used to understand or quantify the heat exposure of massive population based on the anonymous GPS trajectory. So we can conduct simulation every 10 minutes at 1 meter resolution. You can generate and understand pedestrian level and how people are exposed to heat and what that distribution, and maybe in future also check how to mitigate that and how to intervene and really make a difference. So I think the final project I want to talk about is very quickly, it predicts the pedestrian flows. Actually, this is based on my collaboration with my colleague, or former colleague, and also my friend, Andres Sevcuk, he's professor at MIT DASP. So he's the expert in this area to predict the pedestrian flows. So for example, here from origin to destination, theoretically, you get many, many possibilities. You can run different routes. But you may ask, which route do people prefer and why people prefer that? And in other way, can we predict people's preference from one place to another place? So, well, here theoretically they get 84 options with all equal distance. Sometimes the distance itself cannot explain everything. So you probably also need to consider about some other street level features. So in this case, we want to check what kind of streetscape features may impact human preference. Can we really make a prediction based on that? So we use the data. I think I show you about the data in San Francisco. So here there are about 153,000 pedestrian traces with walking distance of 200 meters to 1 kilometer long. So they kind of regular walking distance for most people. We also built a kind of method. Well, if you check more detail, you can read more about this. Andres, he did a lot of this kind of analysis. So we consider many factors like length of streets, whether the highway or not, whether the kind of public art along street, what sidewalk width, scattering factor, green view index, speed limit, traffic volume, and many, many kind of street level features. So we use a green view index. So here I think I already showed you about how to calculate green view index. It represents the greenery level at street level. So here is the street level green view index in San Francisco. And we also calculate sky view factor to represent the openness of sky. And here is the street level sky view factor map in San Francisco. And we also consider about alternative routes. Like for example, if you use Google Maps, you may find they give you three options, usually give you three options. So we also use that as alternative route and check what people actually choose, what the different from the theoretical route and the actual route. We can use that to make prediction and train our model. So we use nominal logical choice model to do that. So, and based on that, we can further, probably recalculate the catchment of different stations. Like in this case, we can, calculate the perceived or the work shade of the BART stations in San Francisco. So with consideration of streetscape features, other than just consider about distance, but also consider the street level amenities or some other PUI point features. So maybe in future we can use that to make prediction about how pedestrians choose their route, how predict the pedestrian flows, and when you plan your city, design your street, you should not design or plan for the cars, right? We plan the city for people. So using that, we can make prediction, also conduct a pedestrian level analysis based on different design or planning scenarios. All right, that is for my presentation. I may go too quick because I have too much thing to introduce. So I go a little bit quicker. So I use a lot of picture to show you the visual examples. So if you're interested, go to check my website, Urban Spatial Informatics Lab, and Temple University in the summer. It's going to be at University of Pennsylvania at Penn. So I would thank to the funding from National Science Foundation and NASA, and also a startup I'm doing, Biometeus. Great. Thank you.
Thank you, Dr. Lee. I think this is wonderful. Yeah, thank you. I think all the issues you talk about today, like the greenery and also like exposure, as well as the walkability, these are all relevant to our daily life and very important issues in the planning and also urban sustainability. Thank you. So now it's time for the question, and we do receive one question. If you can open the question answer box. So from Dr. Hu Tao. I think there are two questions, and then others. Yeah, please feel free to raise your hand or also type the question in the QA box. So either way, thank you. Yeah.
The first question is about whether you have any connection with the local stakeholders, such as the health department, to translate the findings into practical policy to prevent heat illness. The second one is focus on urban heat. What do you think about resilience in rural community? Well, they are both very good questions. For the first one, for the stakeholders, actually, well, I have some connection with Office of Sustainability in Philadelphia and also Department of Public Health. So currently they are using the heat vulnerability map that generated from the land survey temperature. I propose and also, mention that method probably not good. Actually, we are working on, refining or probably upgrade the current heat vulnerability map based on the new heat metric we generate at much higher temporal and spatial resolution. Yeah, it's kind of ongoing work. The second one, focus on urban heat. Well, I think the methodology can be used for any place in the US. Well, not just US, but also the place that have the high resolution landscape data available. So because the model is super efficient, like for example, if I run for the whole New York City with spatial resolution of 1 meter, so it probably just take me about 1 hour for the whole city. So it's pretty efficient, it's scalable, so it can be used for any place. It doesn't have to be in big city, can be in rural communities or small towns as well.
Thank you. Yeah, this is good answers. And any others? Yeah, please feel free to. Yes, okay, I do see. So let me 1 second. 17 yeah, I will raise you to the. Please, now you can talk. Yeah, you can unmute yourself.
Hello, thanks, Dr. Lee. I very prefer your presentation, and I have a question about when we predicting our travel preference. Which method do you prefer, the multinomial regression or agent-based learning? So, I say using agent-based learning modeling or some reinforcement learning method maybe can regression better?
That's a good question. Well, frankly speaking, while I'm not expert in this area in predicting the pedestrian flows, so actually did my kind of based on collaborative work. Andres, at MIT, Sevzug, he's expert in this area. So personally, I prefer to working with this kind of people because I can generate the metrics. I think the metrics can be used for many applications, and he's expert on using the model to predict pedestrian flows. It's kind of very good way for collaboration. So I cannot answer this question. So you can read the paper for more details, or you can also consult some other person who are really expert in this area.
Okay, thank you for your suggestions. Thank you very much.
Great. We do have time maybe for one more question, if anyone. Yes, Professor Mulan, also our CPGIS current BOD chair. Yes, Professor Mu, I think you can. I think you are able to.
Can you hear me?
Yes.
Yep, we can hear you.
Yeah. Thank you, Xiaojiang, for the wonderful talk. Sorry, I'm late, so I missed maybe the first 15 minutes of your talk, but I will look at the video recording after Qiusheng posted it online. So first of all, congrats, and I saw Song's posting in the WeChat group. Congrats on joining UPenn this coming fall. I think UPenn is a place where it holds a very important role in GIS history, exemplified by Dr. Inma Carr's work in the late 60s, early 70s. His very famous social minimum cost alignment, or AKA the overlay method, influenced the generations of GIS researchers. So what the beauty about his method is his method or his case study actually changed the real world, right? So like his decision, the conclusion from his research project actually changed the decision of how the Richmond Parkway is constructed. So I guess my question to you is this all kind of wonderful data, fabulous like models and calculation analysis. So how do you see maybe in the long run, like this research can change the way we do things in the real world? Thank you.
Yeah, thank you. Well, this great question, and thank you for introducing Meg Hager and give us introduction about history at Penn. Well, yeah, I get a chance to meet with many people, many of my Harvard students at Penn as well. I also do some work out in this area. Yeah, a great person and has a great impact on GIS world. Well, I really appreciate this kind of work, you know, really make a difference, make our world different. So, well, personally, actually, I prefer to kind of, you know, you may find a lot of my work and not new questions, but I prefer to use new way to solve the old problems. So for the greenery, we use a lot of traditional methods like top-down view. Then they're just not human-centric. We use kind of, you know, the bird view or top-down view. It may good to quantify the physical presence of tree canopy cover, but not human-centric. It's not really related, not much related with how humans really feel. So for the green view index method, it probably been better for public health work to guide the design of streetscape and landscape design as well at the hyperlocal level, at pedestrian level from human perspective. So for the heat map, you may find the not big new question as well, but probably a much bigger question now. So traditionally, we tend to use a remote sensing based method, but you know the land survey temperature is not human heat stress, and a lot of time we tend to use easier method to generate the map. We find, you know, we can generate that very quickly, but it doesn't mean it's good or the right to use a method for our real world studies. So that's the reason why I propose to use this kind of high-performing computing method and generate at the hyperlocal level, spatially and temporally. So and also from more human-centric perspective. So that definitely going to make well, I think I hope it could make a big difference to our community in this area. So I'm trying to promote the method and share the methodology and also share the data set with the community, and hopefully it will make a difference and make our city, or not just city, but more places, you know, more resilient to extreme heat in near future. Thank you.
Thank you.
Yeah, thank you, Dr. Wu and also Dr. Li. Yeah, I think this is wonderful. And also, I think that's also concludes our webinar today. And thank you very much again, Dr. Xiaojiang Li, and congrats again. And so I do want to remind the audience, thank you for joining us today. And also our next webinar will be next Friday. So from Dr. Rui Zhu from Singapore. Yeah. Thank you, everyone. See you next week. Bye-bye. Thank you, Xiaojiang. So,
yeah, sure.
Are you joining AAG?
No, I'm not going to.
Okay.
AAG
Then I will see you in another time. Yeah. Thank you.
Yeah, sure. Yeah.
Bye-bye.
Take care.
Thank you. Yeah.